What if I turn around like this? I really can't see what you do, right?
I think this desk is the only desk that if the person turned around, you can see. Okay. So, mean value theorem. Today we're going to talk about two main theorems. One of them being the mean value theorem.
Is the other one the median value theorem?
No.
It's
The mode value theorem.
I'm glad you guys know what it means.
the average.
Oh my
And you
goodness.
didn't think it was like
Oh,
some like Grinch theorem or something.
this is gonna be
I'm
like.
going to be so rude today.
Happy holidays.
Mean value theorem.
Listen,
This crowd.
Huh.
Watch, you're gonna like record stuff of like things moving, like there's ghosts in here.
Oh my God.
Okay, that was fake.
There's no ghost.
Fair, talk about it.
Okay.
Make a presentation last year. The issue is fake.
Mean value theorem. So, first we're going to talk about Rolle's theorem, which is, okay, so Rolle's theorem, you have to have a function with these three characteristics. So anytime we have a theorem, there's usually characteristics attached to it. The first thing with our function is that it has to be continuous on a closed interval. The second thing is that it has to be differentiable on the open interval. And the third thing for Rolle's theorem is that the function evaluated at the start of my interval f of a has to be equal to the function evaluated at the end of my interval f of b. And if those three things are true about a function, then that means there has to be some number in that interval where the derivative is equal to 0.
Good job, man.
So if they were to drop something like in the middle,
Oh.
you guys are acting weird now. I should have not said anything. I suppose I need to just get those waivers and then we don't have to worry about it. You
Is that F primacy?
No.
can, yeah, right here? Yeah. Okay, so one more time. These three things have to be true. So the function has to be continuous on the closed interval that we're looking at, this interval that goes from A to B. It has to be differentiable on the open interval. Keep in mind, like visually, visually, if I have my graph here and my function goes like this, is this continuous from A to B?
No. Yeah, no.
Yes, it's continuous. It has every point identified from A to B. Is it differentiable on this at every point on this interval?
No.
Where is it not differentiable? Right, this is called a cusp. So remember back in like chapter 2, I think we talked about how a function fails to be differentiable. And this would be one of those cases. So that's when something is continuous, it is still possible for it to not be differentiable. And that would be why you need to check for both of those things. Stop talking. So it has to be continuous on the closed interval, which means the endpoints have to be included when you check for continuity. It has to be differentiable on the open interval, and the function evaluated at the start of your interval has to be equal to the function evaluated at the end of your interval. If these three things are true, then Rolle's theorem tells us there has to be a point somewhere in there where the derivative is equal to 0. Okay, so that is Rolle's theorem. and some visuals for that. Purple lines are so hard to see. This first one here, we have a constant function k. And if we wanted our interval to go from a to b, then the function evaluated at a is equal to the function evaluated at b. And anywhere in there for this problem, the derivative is equal to 0. But we do know that at least somewhere in there it has to be equal to 0. Over here we have part of a parabola. Okay, and we've started our a. We've chosen the point that matches the function evaluated at b. You see that? So the function evaluated at a is equal to the function evaluated at b. And we can see that in here, we have a point where the tangent line, the slope of the tangent line, would be equal to 0. So our derivative is equal to 0 somewhere in there because the function evaluated at a is equal to the function evaluated at b. Does that make sense?
So f power c has to be 0.
Somewhere. That's what Rolle's theorem says. As long as these three things are true.
Oh,
Okay, in this one here,
I see.
if we start our interval right here, this is point A, and then we end our interval over here, we've picked 2 points where the function evaluated at A is equal to the function evaluated at B. We know that we have a continuous function, we have a differentiable function, and these are equal to each other. And so there has to be at least one point where the derivative is equal to 0. In this case, we have 2 points where we have the slope of the tangent line is 0. Does that make sense? So again, we start with the visual, we're going to get to the mathematical.
For the second one,
Yep.
how is the function evaluated at a equals
Because A starts right, A is here.
Oh.
Even though the function is all of this, we've chosen a point for A so that this is true. Okay? Other questions? Same thing is happening right here. We have our interval from A to B. The function evaluated at A is equal to the function evaluated at B, and so we have the slope of a tangent line that is equal to 0 somewhere in between there. Any questions on that? Do you guys understand the idea behind this? No?
I,
I couldn't really see it.
So do you have questions? Like if you don't understand it, that's not good.
So this is the theorem?
This is the theorem. You check for these 3 things. If these 3 things are true, then there has to be something in between here where the tangent line is equal. The slope of the tangent line is equal.
okay, I get this little bit of part.
You sure? Okay. Here we are. Okay. So here we have a person on a 20-foot cliff, throws a ball straight up into the air at a velocity of 64 feet per second. The equation, blah, blah, blah. This is our position equation. Here, this right here is the graph of the position of the ball that's being thrown off the cliff. So the person starts right here at the cliff that's 20 feet, throws the ball up, and then it eventually goes back to the ground. We want to show that the velocity of the ball is 0 at some time between 0 and 4 seconds. So, if we want to prove this before looking at a graph, what do we need to show? Okay, we need to show that it's continuous between 0 and 4. Is this function right here continuous between 0 and 4? How do we know? Because it's a polynomial, and a polynomial is continuous everywhere. So it wouldn't matter what our function is, or what our interval is, it's continuous everywhere. What's the next? Yeah.
4 isn't inclusive, right?
Well, you would have to include 0 and 4 in continuity. But if we're talking about a polynomial, it does not matter what these numbers are because they're all going to work. Because a polynomial is continuous everywhere. Okay. What are some times when we may have issues with continuity?
Absolutely.
If it has a denominator, does absolute value lack continuity? Just differentiability at the b, but not continuity.
How does it is a limit?
Say that again?
A limit?
What about a limit?
Like, you saying that it's not continuous, what about the limit?
A limit is like how we evaluate a function. I'm asking about types of functions where we deal with discontinuities. And that would be if we had a denominator in our problem where the variable was in the denominator, we're going to have some points of discontinuity. What other types of functions have discontinuities in them? Or can have discontinuities in them, I should say. Square roots can have discontinuities in them. And why is that? What do we know about square roots?
They have a negative
They
index.
can be negative. Yeah. Okay, so again, I referenced this yesterday, but what we talked about in chapter 2 about different functions that are continuous, talking about things being continuous everywhere, that's going to be important to know the more theorems we learn, because a lot of these theorems are based on continuity. So we know that it's continuous. That's our first step. What else do we need to know? We need to know if f of a equals f of b. What else?
That
Out of
the
C
function
was
is
0.
differentiable.
We have to know that the function is differentiable. What you're saying is the conclusion after we've proven those three things. So we know it's continuous everywhere because it's a polynomial.
Yes.
We know that it's differentiable everywhere because it's a polynomial. Okay? So then we need to show that f of a is equal to f of b. What is a for this problem?
1.
A is equal to 0.
And B is equal to 1.
B is equal to 1.
Why is it A equals 1?
B is equal to 4.
Oh,
I was
that's
thinking
nice.
that wasn't going to match, but it does. Dang, too easy. Okay, so A is equal to 0, B is equal to 4. How are we going to prove the third part of Rolle's theorem?
Plug it into the equation.
Plug it in. So I'm evaluating my function at 0, which means I plug 0 into this function, and what do I get when I plug 0 in?
20.
I get 20. And then I have to evaluate my function at 4. And when I evaluate my function at 4,
20.
we're going to get 20.
60.
So because those three things are true, then there has to be a point somewhere where the velocity, and what is velocity in terms of calculus? What was it?
Derivative for slope.
It's the derivative, it's the slope of the tangent line, it's the rate of change of this position function. So if it's asking about the velocity, then we're talking about a derivative. We know that at some point in between 0 and 4, the derivative has to equal 0 because of Rolle's theorem, which means the ball stops moving at some point. Make sense? You guys have any questions on that? Do you understand?
Yeah.
What don't you understand? This is the answer. This is all the answer. You have to show that these three things are true. If these three things are true, then the velocity has to be 0 at some point. That's all you're
So all
doing.
you
It's the type of questions we'll have.
Or do we have this?
So we don't
solve?
Some of them might be like this.
We don't need a graph.
No, the graph is a nice visual, but you don't actually need it. because it's a polynomial, it's differentiable everywhere. I do believe that was also a box we did in chapter 2, maybe? So we talked about types of functions that are differentiable in certain domains. That's what you need to know. We just plugged them in. So we did the starting point of your interval and the ending point of your interval. All right. So the mean value theorem kind of builds off of Rolle's theorem, but it allows us to kind of expand our thinking about these slopes of tangent lines. And mean, what is mean? What is a mean? A mean is an average. Okay, so that's what we're dealing with here is an average. And what the mean value theorem is based on, first of all, is that our function is continuous on a closed interval. Okay, so just like Rolle's theorem. And that our function is differentiable on an open interval, also like Rolle's theorem. What the mean value theorem gets rid of is the fact that f of a has to be equal to f of b, which is no longer true. Okay? What the mean value theorem tells us is that there's going to be some point in the interval that we're given where the derivative is equal to the average of these two values on the endpoints. Or there's going to be a derivative at some point in the interval that is equal to the secant line between the two endpoints on the interval, the slope of the secant line.
So it's like just it's like
That you're taking part of that from a limit definition, which it's not, because when we're talking about f of x in the context that you're talking about, that's actually the function. In this case, we actually have numbers. We're working with all numbers. So f of b is evaluating my function at the end of my interval. That's what you just asked.
It's more of a slope, is what it is.
Right.
Because it's the slope of the secant line between the 2 points.
So. So what's the difference?
Say that again?
What's the difference between continuous and closed?
There's just, it has to be continuous on the closed interval, so the endpoints have to be included in continuity. So you can't have like an open endpoint with these intervals. Something can be differentiable all the way up to an open interval, so that this is the last thing we're learning today. We're just going through examples. So let me give you your homework. Try. 1 through 25, every other odd, and then 34 and 35. Are they free? ready for examples? Do you have questions on the theorem? The literature? We use this theorem to find certain points in our interval where a slope is equal to the average slope, or where it's equal to the slope of the secant line. All right. Huh? I'll cut it out. I'll figure it. I'm gonna get you guys those papers. Alrighty. So graphically, a pictorial representation for you. If we have this part of our function here, we're looking at the interval from A to B, then the slope of that secant line visually obviously goes through our endpoints of our interval. And what this theorem tells us is that there is a point somewhere in there where the slope of the tangent line is equal to the slope of the secant line. And this will always happen. There will always be some point from here to here where these are parallel lines, where the slopes are equal to each other. So if we can identify the slope of our secant line, then we can start to find points, bless you, start to find points in our interval where the tangent line is this value. And this average value becomes important when we talk about like average rates of change and that kind of thing. Okay. So visually, this is what we're doing. We're finding this other line that's equal to our secant line. Can I go on?
Yes.
Here to know. Good? Okay. All right. So here we have our endpoints A to B, the slope of our secant line between these 2 points. And somewhere in between there, we have at least one tangent line that has the same slope as this one secant line that we've already identified. So again, we start to identify where it is that these are happening because we know the average rate of change over the entire interval. Okay? Alrighty. Find a number c for the function y equals x to the third minus x on the interval 0, 2. And we're trying to find it using this mean value theorem here. So, before I can even apply this theorem, what are the 2 things I need to know?
Is coordinate
If it's continuous.
continuous?
If it's continuous, is this function continuous?
Yes.
How do we know?
It's a polynomial.
It's a polynomial. Polynomials are continuous everywhere. Differentiable. Is it differentiable? Yes, it's a polynomial. Polynomials are differentiable. So because of that, we can use this here, our mean value theorem, to prove that we have a slope at some point that's going to be equal to the slope of the secant line. So the first thing we want to do is we want to find the slope of the secant line. We want to be able to identify that so that we can eventually get to this point C. Okay? So the slope of my secant line, I'm evaluating f of b, and what is b in this case?
X to the
What is b in this case?
2.
B is 2, it's the end of my interval. So if I'm evaluating f of 2, actually let me just write this. Minus f of a, what is a in this case?
0.
A is 0. Over b minus a, so 2 minus 0. And I need to evaluate f of 2, so what is f of 2?
6.
And f of 0?
0.
how does that choose three?
You plug 2 into your equation. 2 cubed is 8.
Oh.
Minus 2 is 0. So I get 3. What did I just find? What is 3? It's a slope of the secant line. So I have the slope of the secant line from this point to this point on my graph. And this tells me that somewhere in between 0, 2, I'm going to have a tangent line that has that same slope. I'm trying to find what number actually has a slope of 3. Okay? How would you go about that? What number actually has a slope of 3? What do I need to know if I'm talking about slope over an interval?
The rate that it changes the line.
What do I need to know related to this? I have to know a derivative if I'm talking about slope. Right? So what's the derivative of this function? 3x squared minus 1. What value for the derivative am I specifically looking at? 3. I'm trying to find where my derivative equals 3. Right? So I'm plugging in 3 for y prime. And it's asking me to find the numbers where my slope is equal to 3. So I'm trying to find out what x values are, or at what x values is this slope equal to 3? Is the derivative equal to 3? So what am I doing with this?
Solve for x.
Right, solve for x. So first thing I do to solve for x,
You add
1,
4,
divide by 3,
Plus or minus the square root of 4. You get 2
square root of 4 over 3.
Then you can,
and then
it might be like, maybe 2 over square root,
Okay, do I want to leave it like that?
right? No, so it's 2 square root of 3 over
How do you get there?
Wait, how do we get 2 over square?
Because the square root of 4 is 2.
Oh, okay.
So you know, will always running issue, so this can you say like the next part after finding f prime c, once you get 3 equals this part a.
We're trying to find the point where the derivative equals 3 because we need a tangent line that has a slope of 3, which means we have to derive the equation. Once I derive the equation, I substitute 3 for y prime and solve for x. So how'd you get there, JJ?
3. I don't know, just.
You don't know how you can just magically guess 2 square
Well,
root of 3
no,
over
I
3?
know how to do, I know how to do that.
Multiply.
2 over 3.
Multiply by the common.
Multiply by itself, square root of 3 over 3.
Oh, yeah.
So I get 2 square root of 3 over 3. So what did we just find? What is this plus or minus 2 square root of 3 over 3?
That's.
where the tangent line, or has a slope of 3.
Where the tangent line to this curve has a slope of 3. We want to know numbers or x values in there where the instantaneous rate of change, get used to these kinds of words, where the instantaneous rate of change is equal to the average rate of change over that interval. Okay? Kind of a real life thought process of what's happening here. If I'm going to take a trip to California, and California is like 300 miles away, if I get there in 5 hours, I know that I went an average of 60 miles per hour, right? Can you guys handle that? 60 miles per hour was my average. If 60 miles per hour was my average speed from here to California, then what that says is at some point in those 5 hours, I had to have been going 60 miles per hour. At some point. I could have driven 80 miles per hour for 3 hours, and I could have gone 50 miles per hour for another hour, but at some point in there I had to be going 60 if my average speed was 60 miles per hour. Does that make sense? So that's what's happening here. We find an average rate of change, and we're proving that at some point that average rate of change has to equal those instantaneous rates of change. Those moments. Okay? Did you have a question?
Yeah, I know you probably explained this, but how did you get to the square root of 3? Did you do like square root of 4 or square root of 3 and then do it?
Other questions on this? Yeah.
So the plus or minus 2 square roots of 3 over 3 is the instantaneous?
Those are the x values where the instantaneous rate of change is equal to the average rate of change. So if I'm looking at the graph and I go to, let's say this is like, let's say this is close to 1, plus or minus 1. Then when x is equal to 1, the slope of the tangent line there is going to equal 3. And when x is equal to negative 1, the slope of the tangent line there is also going to equal 3. So I'm finding these, which means that we shouldn't include the negative number. Does anyone know why we shouldn't include the negative number? I just thought. What interval are we looking at?
0 to 2.
Oh, 0 and 2. So
0 to
that would
2.
not be negative.
The negative x value doesn't matter
But it's not positive.
because we're only talking about the interval from 0 to 2. Okay, so just positive 2 square root of 3 over 3.
You take a square root, so plus or negative, it just doesn't apply to this
Okay,
problem.
There really is a negative answer, but we don't use it. It's not in our interval.
This problem.
If the interval was bigger,
Yes, yes.
Yeah, that's right.
All right,
still right.
so a couple things to recap.
Right,
If we're
this
going to
problem.
use the mean value theorem, what has to be true?
Your good question.
If we're going to use the mean value theorem, what has to be true?
F has to be continuous.
It has to be continuous. On a closed interval.
F is differentiable.
Differentiable.
It has to be differentiable. So those two things have to occur in the interval. Okay, if I have a function that's not continuous, but I'm only looking at an interval where it is, then I can use it. Okay? And what is this idea of the mean value theorem? What is it telling us? There's a tangent line. Good. There's a tangent line with the slope that's equal to the slope of the secant line. Okay, so the average rate of change equals the instantaneous rate of change at some point. Talk to me a little bit about the process. How do we find these numbers C?
Wait, what about the F of A equals F?
That's the Rolle's theorem. You can only use that if f of A equals f of B. Did f of A equal f of B here?
No.
No. So because of that, you have to use the mean value theorem. So what was our process here to find this number C?
Find the slope of the secant line.
Okay, we started by finding the slope of the secant line. Once we found the slope of the secant line, then what did we do?
Take the derivative of the function.
Okay, we found the derivative of the function. So we derived this here. And what did we do with that?
Plug in the slope of the secant line for y.
We know that this secant line has to equal this derivative at some point. So we're going to plug it in. And then what do we do?
So
Solve for x. So there's your process for finding those numbers using the mean value theorem. Yes?
And is that the point where if you plug it in, the slope of the tangent line equals the slope of the secant? Or is that-
Yes. If you keep in mind that, like, yes, if you can think about this visually, this is the point on the graph where that line, they're parallel then. The secant line is parallel to the tangent line. So you're not actually going to plug this into your function to get, that's just going to give you a y value. That's not going to give you any information. But yes, the slope is equal to the secant line at that point. Other questions on the mean value theorem? Okay. I'm going to give you guys your assignment. Please start working on it now so that you can get questions answered now.
Are there any problems where we're gonna have to be able to tell if they're differentiable or not, and not using polynomials?
No. They're all, I mean, they're pretty standard functions that we work with. Most everything we work with is different. I don't know that we've seen. We don't really see functions that like come to those unless it's like a graph that's drawn. Yes. Did you have a question?
Yeah, where's the f of b minus f of a, was that prime c times b minus a?
That's just rewriting this function right here. So you've multiplied both sides by the denominator. And it's just another way to use it. If you're solving for a different part of if you're solving for a different variable or something, it might be easier to work with that.
So if we use that with the circle,
Yeah, it's the same thing. She wrote? Oh, she looked in the, I know, it's not. So did Dr. Schwartz. Did you see him?
yes.
Yeah.
It was right as like you asked a question that everyone.
Yep, and just kind of stared and then
You just got in charge of saying something.
All right.
Saw me sitting on your floor.
Your assignment is 1 through, did I say 1? Yeah, 1 through 25, every other odd. And then 34 and 35.
So 1 through 25.
34 and 35. Yep. Yep.
34?
34 and 35.